Okay, go ahead. You can start.
Okay. It is my pleasure to be a speaker in this workshop. Thanks for invitation. I will speak about fractional characteristic functions and fractional moments of random variables. The results are prepared jointly with Professor Ralph Metzler and Professor Stefan Gerhold, supported by that foundation. The talk will be separated in three parts: fractional characteristic functions, how can we express the fractional moments via fractional characteristic functions, and their applications. The main objectives are to introduce a fractional variant of the characteristic functions of random variables, to express fractional moments in terms of the fractional calculus operators like Riemann-Liouville, and derivatives of the fractional characteristic functions. Then we will give some illustrative examples for fractional probability density function whose associated integer moments don't exist. We know in classical probability theory for the given random variable x and with associated probability density function, characteristic function is a mathematical expectation of these exponential functions and can be expressed by these infinity integrals of Fourier type, where P of x is a probability density functions. These functions can be also expanded in Maclaurin series in respect to her integer moments, mathematical expectations of integer moments of the random variable x, where can be expressed as integer derivatives at the point 0 fractional characteristic functions. We introduced a new definition, new extended definition, how can be defined fractional characteristic functions. For fractional parameter between 0 and 1 of random, for the random variable x of real variable. So it is defined via Mittag-Leffler functions with one parameter e tx power alpha of times probability density function. This is an infinity integral which generalized previous classical characteristic functions. And here, because at the point 0, characteristic Mittag-Leffler function is equal to 0, the value of the fractional characteristic function will take value also 1. And for alpha equal to 1, it is a classical case that this fractional characteristic function is equal to the classical characteristic functions, and the conjugate functions is equal to the function of minus t. Moment generating functions, we know that it is also very applicable function in probability theory. We define here fractional moment of moment generating function of order alpha between 0 and 1, and it is in an analogical way. It is defined via infinity integral of Mittag-Leffler functions with one parameter times probability density functions of the random variable x. Next, we will give some connections between two functions, between characteristics, fractional characteristics and fractional moment generating functions. For non-negative random variables, it is real valued on the real half axis. For alpha between half and 1, characteristics, fractional characteristic function and fractional moment generating functions are connected with this relation. M alpha of t is a fractional characteristic function of the exponential minus e p over 2 alpha times where t is non-negative real number. And this equation is true because of the equality given below, which holds under the inequality argument of the variable t is greater than p times 1 over 2 alpha minus 1. This is a relation between two functions. Some proposition of the defined functions, fractional characteristic function, we prove that the fractional characteristic function exists for all real number t variable. Then the fractional moment generating function exists exactly for those real variable t for which the classical moment generating functions exists. The proof of this proposition follows by the asymptotical expansion of one parameter Mittag-Liouville function with the exponential functions of tx. And from here, we know that if moment generating function does not exist, then the fractional moment generating function, it does not exist for real number t. Also, we prove as a generalization of the classical proposition that characteristic functions in uniformly continuous function on the real line. We also prove that the fractional characteristic functions of any random variable is uniformly continuous on R. These results are proposed and submitted for publication in the journal Fractional Calculus and Applied Analysis last year. And the proof of the proposition are presented there. So in this presentation, I will omit them. I would like to mention about the Zhivorad paper, which is wrong. We will comment one paper in our reference list, which defines the fractional Laplace transform via this integral, alpha limit of this integral 0b of the real line minus b minus x power alpha minus 1 times Mittag-Liouville function of this power function times f of x, where f is Lebesgue integrable function on the segment AB. So Zhivorad does not mention any probability interpretation of this integral, but our definition is analogical translated in the probability language. So for alpha between 0 and 1, any function with bounded support, such as density of a bounded random variable, has a fractional Laplace transform that is identically 0 under this definition, which raises doubts about its usefulness. Zhivorad proved the existence of fractional Laplace transform formula by using this identity that Mittag-Liouville function of this binomial function x plus alpha power alpha is the product of this two Mittag-Liouville function, which does not true. It is false, this identity, which is true only for alpha equal to 1. About the detail of this identity and counterexample, we can consult the paper of Peng Li. This is the second paper of our the reference list. So the paper of Zhivorad is not true, although it is also cited by other authors which worked on the fractional calculus operators. Example, how can we use this fractional characteristic function to express by using their probability density functions. For example, we will consider a Cauchy type distribution, P of x And if we choose the function g of x to be Mittag-Leffler function of the power function x alpha times imaginary unit, then by using Laplace, by using a Mellin transform of for both function, for the Mittag-Leffler function and for the Cauchy kernel, by using the convolutional equality of Parseval this equation is this connection convolutional for integral convolutional theorem of Parseval can be found in many books. I have consulted the paper of Luchko and Kiryakova published in 2013, and they also use this formula to found many infinity integral of some fractional special functions of Mittag-Leffler H functions, and also they use them to analyze some probability problems. Okay. So the characteristic function, fractional characteristic function can be expressed by this Mellin-Barnes integral representation. By definition, it is a Fox H function with the parameters that is appear in Mittag-Leffler function and in Cauchy distribution. So in this case, characteristic function of fractional order exists, but the moment generating function of fractional order does not exist because, as we mentioned before, Mittag-Leffler function of fractional order is greater than this exponential function over x squared. So because this integral is divergent and moment generating function also is divergent, so characteristic moment characteristic function is in divergent function in general case, and this counterexample shows us that fractional characteristic functions is better function in some modeling of probability random variables process, and also applications in fractional stochastic processes and in modeling by partial differential equations in fractional diffusion processes. So we will consider any one interesting example about Levy flight density function. Mainardi, Luchko, and Paganini consider space-time fractional diffusion to express the solution in an infinity domain and obtain this function where alpha is a parameter between 0 and 1, and it is called stable index of the density function, and theta is skewness or asymmetric parameters of this Levy distribution functions. Also, we obtain this function as a solution of space-time fractional diffusions by using Hilfer fractional derivative operator. It is published in collaboration with Trifce Sandev, Ralph Metzler, and Johan Dubeldam in Physics A, Statistical Mechanics and its Applications in 2012 years, 10 years ago. So this Levy distribution is with this parameter alpha between 0 and 1, and it can be also written in another form when alpha stable index is between 1 and 2. In this the next relation, where it's appear constancy in the both case, and theta is less than with absolute value of 2 minus alpha. So we will compute the positive characteristic function. In this case, the Mellin transform is proved by Mainardi and Paganini in 2008, and it is expressed via gamma functions. So to compute the fractional characteristic function, we will use upper fractional characteristic function denoted by plus, where we only integrate over real positive part. And assuming that rho is between 0 and 1, we refer to the paper of Mainardi Paganini in 2008 for detail. The fractional characteristics functions can be also expressed of the Lewis stable distribution as H functions with this parameter alpha and C. The next one open problem is how to compute moment generating function, but we can use the relation that I mentioned previous. About the fractional moments, we know that for integer case, fractional moments can be expressed via classical fractional characteristic functions. And here, for the fractional moments, don't grow too fast because of the inequality of the absolute value module is less than of power of C k times gamma functions of alpha k plus 1. About this inequality, the fractional moment don't grow too fast. And then there is a pure fractional power series expansion of the fractional characteristic functions via this fractional characteristics, fractional moments of the fractional random variable x alpha by using Maclaurin expansion of the alpha plus k. By using the fractional calculus operator of Riemann-Liouville type, you express formulas for fractional moments via these fractional operators. We will present it here. Other representation of the differential operator of Riemann-Liouville is given by Hilfer in 1998 by interchanging of the integrals given in Riemann-Liouville integral. And he expressed the Riemann-Liouville integral in this form, form 2, which is very good to apply to compute our fractional moments of order gamma. So we obtain a proposition. In detail, the proof is given in submitted paper. When gamma is positive and less than alpha, then the double integral is absolute convergent. And we obtain the following two relation between fractional moments of the random variable, fractional moment of order minus gamma. In first case, minus plus minus gamma, it is expressed by the Riemann-Liouville at a point 0. And in the second case, with positive gamma, it is expressed via fractional derivative operator of Riemann-Liouville type in the point 0. This formula generalizes the formula, which is proved by Cotone, Ralph Metzler, and Paola. The paper is published in 2010. It is 8th reference of my list. And the special case for alpha equal 1, it is their results. By application of the relation for a fractional Riemann-Liouville integral and differential operator for the fractional characteristic functions at the point 0, and Mellin transforms for these functions, we can obtain formula, explicit formula for the fractional characteristic functions in respect to their fractional generalized moment. where it appears some transcendent functions, and it is expressed as Mellin-Barnes integral in respect to the order of the fractional moment gamma. And here also another formula, minus alpha, where U is positive and the integrals are performed vertically with fixed real part rho, belonging to the so-called fundamental strip of the Mellin transform of the function phi alpha. The later equations are integral extensions of the first equation. And special case for alpha equal 1, this formula for the probability density function via their fractional moments is founded by Cotone-Metzler, and this is inverse Fourier transform in respect to their fractional moment, and the integral is in respect to the order of the moment d gamma. How we can apply this formula to express fractional moment by application of the results obtained for the fractional characteristic functions. So we will consider this probability density function of Mittag-Leffler type. This function's a Mittag-Leffler function of -6 power alpha for alpha between 0 and 1. It's defined by Pollard in 1948, and Mainardi 2040 proved that this function is positive function for x positive, or this is a probability density function, because the Laplace transform of this function will be equal to term for x for s equal 1 will be, the integral will be equal to 1, and this is a positive, and because this is a probability density function, we can use it as a P of x, and g, it is a Mittag-Leffler function of the exponential variable. By application of this Parseval convolutional equality, we can express fractional characteristic function also by using Mellin-Barnes integral representation, definition of for h function. It is h function, and to apply the fractional moment, we have to compute the fractional Riemann-Liouville integral as a Mellin integral representation. Similar problem are investigated by Mattei, Saxena, and Haubold in 2010, and by application of the proposition 3 times 4 in the Mellin transform formula for the h function, the Riemann-Liouville integral is given by this term, and from here by the last proposition, the fractional moment of order minus gamma is this function of the product of many gamma functions and trigonometrical function. Next example, we consider Mittag-Leffler Whiting time density x alpha minus 1 times 2 parameter Mittag-Leffler function alpha alpha. For x positive, this is also positive function, and the integral of this function is equal to 1. This is introduced by Hilfer and Anton, 1995. To express the fractional moments of this probability density function, we use also Mellin transform, also obtained by Mainardi and Mainardi. We use this function and apply a convolutional Parseval formula and Mellin-Barnes integral representation. We also obtain elegant h functions with parameter alpha. Also, we compute a Riemann-Liouville integral of order gamma for the fractional characteristic function, we obtain this term, and finally we obtain short formula for the fractional moments. The reference list take 12 reference, and there are also some new papers and book published by Tomovski and Sandev, minority papers that created meta-characteristic function and their complete monotonicity properties. Cotone, Paola Metzler paper published in Physica A. The main paper is also Luchko Kiryakova, Mellin transform in fractional calculus. The rule of the Mellin transform formula in fractional calculus. And this also motivated me to consider this paper. And what to say at the end, that the motivation is that fractional moment is very used in dealing with random variables, which probability density function is asymptotically equivalent with the power function of order mi. And if q is integer is less than mi, then the integer moment exists for this function. But for q greater than mi, the integer moment are divergent. I can close the lecture, and
Okay.
if you have interest for any question, I'm able to give you my explanation.
Okay.
Thank you.
Thank you. Is there any questions? I check if there are online. Any questions? No? I can ask you.
Yes, you're welcome.
Yeah.
Luisa, this is your topic in Sapienza University.
Well, more or less, yes. But is it possible to